Hi, welcome everyone to my presentation for the High Temperature Plasma Diagnostic Conference. This presentation is entitled Development and First Operation of a Cavity Ring Down Spectroscopy Diagnostic in the Negative Ion Source SPIDER. This work is part of the development and test of the ITER Neutral Beam Injectors, which is being performed in the Neutral Beam Test Facility at Consorzio RFX in Padua. In particular, the key component of the neutral beam injectors, that is the negative ion source, is being tested from 2018 in the SPIDER experiment at the NBTF. Here you can see the top view of a 3D model of a negative ion source inside SPIDER. The plasma is generated by means of radio frequency in 8 plasma drivers, and then which are represented in green, and then the plasma diffuses in a common expansion chamber towards a bias plate and then to a system of 3 grids, namely plasma grid, extraction grid, and grounded grid, which have the task of extracting and accelerating negative ions up to an energy of 100 keV. Bias plate and source body voltages and the PG currents, which create a magnetic filter field, help reducing the co-extracted electrons and the negative ion loss by electron stripping. One of the key points in experimentation in SPIDER is to maximize the extracted negative ion current density and its uniformity for plasma pulses that have to last up to 1 hour. To accomplish this, it is necessary to measure the negative ion density close to the plasma grid, and this is possible thanks to Cavity Ring Down Spectroscopy Diagnostic, which is the object of this presentation. First, I will show you the principle of operation of the diagnostic, then how it was implemented in SPIDER, and then the first results of this diagnostic with the recent experimental campaigns in SPIDER. How the CRDS works. A laser pulse is sent to the back of a high reflectivity cavity mirror, and a small fraction of it passes. This laser beam is trapped inside an optical cavity, which is made by the first mirror and the second one. Bouncing back and forth, part of the pulses are able to escape the optical cavity, and the consequent train of pulses has an intensity which decays with a specific decay time τ0, which is given by the cavity length L and the mirror's reflectivity. This decay time can be reduced if an absorbing medium is inserted inside the optical cavity. This is possible because the H- ions absorb the photons of the laser beam by means of a photo-detachment reaction. By comparing the decay time tau with negative ions and the decay time without negative ion and plasma, it is possible to have an estimate of an average along the line of sight of the optical cavity of a negative ion density. So, how CRDS was implemented in SPIDER? The laser providing the beam pulses is a neodymium laser emitting at 1064 nanometers. Each pulse has an energy of 150 millijoules and the pulses are emitted at a repetition rate of 10 Hz. The laser is not located inside the bioshield of SPIDER, but it is outside of it in a small dedicated chamber to be protected from gamma rays and neutron radiation. In the optical board on which the laser is placed, there are several mirrors in order to steer the path of the laser beam towards an aperture which is made on purpose in the bioshield concrete wall. There is also a second laser emitting at 532, a continuous laser, and its purpose is to provide a visible tracer to check the position of the laser beam for the alignment procedure. So the two laser beams are co-aligned, they exit from the concrete wall of a bioshield, they reach the vacuum vessel or spider, and thanks to two mirrors, they reach the main optics on the input side to enter the optical cavity. These are the mirrors and the focusing lengths which deviate the two laser beams towards the entrance of the optical cavity. Here there is the first high reflectivity mirror, and it must act as a vacuum air interface. So there is this structure which ensures the vacuum tightness of the system, and also allows by translation and rotation to perfectly check the desired position of the optical cavity. In fact, the laser beam must pass in the optical cavity through the 10 mm diameter holes that have been made on purpose on the sides of the source inside spider. Here you can see the position of the line of sight of CRDS, that is the direction of the beam inside the optical cavity. You can see that the laser is passing in front of a bottom group of apertures of the plasma grid, apertures from which the negative ions are extracted. The laser passes at a distance of 5 mm from the surface of the plasma grid, and it is in between the plasma grid and the bias plate, which is here schematized in light blue. In this picture, you can see the opposite side instead of the optical cavity. Here there is the output high reflectivity mirror, which is placed in a support structure similar to the previous one, with the only modification that here there is a collimator which collects the laser pulses exiting the cavity and carries the light through a fiber up to the optical room, where an avalanche photodiode detects the light. An interference filter is also used in order to filter out the light that might be emitted by the source plasma and collected by the collimator. On the top left corner, you can see an example of cavity ring down signal, and in red, exponential fit that, as you can see, is in good agreement with experimental data. The first 20 microseconds are excluded from the fitting procedure because at the very beginning of a ring down, multiple cavity modes exist, and they decay with different level of taus. However, these modes decay very rapidly, so after 20 microseconds, the ring down signal can be considered mono-exponential. On the bottom right corner, you can see the time evolution of the measurements of tau. For each pulse, the value of tau is measured before switching of the plasma on and after the switch off of the plasma, so that there are enough values to calculate tau zero. As you can see, the values of tau exhibit a drift with time, which can be corrected for sufficiently short pulses, and I mean pulses of up to several hundred seconds. They can be corrected by using a linear fit, so that tau zero can be estimated at any time during the plasma phase, that is represented here as with the RF power trace. Also, you can see that the measurements of tau have some fluctuations, and these limit the minimum value which can be measured by the diagnostic. The limit for the diagnostic in spider is of 5 per 10 to the 15 negative ions per cubic meter, which is perfectly sufficient in any case to study the behavior of the plasma and of negative ion production, even without cesium. Here I can show you some results that were obtained by Cavity Ring Down Spectroscopy during the spider deuterium campaign in October 2020. The data you can see here belong to a single shot in which the source pressure was varied. And as you can see, the D- density varies almost linearly. You can also see that the absolute values of the minus density are roughly 1 order of magnitude lower than those that were measured in negative ion sources in which cesium is evaporated, and this is perfectly expected. We also saw that the minus production has a dependency, of course, on the input RF power which generates the plasma. Here, the first result is that at least 120 to 180 kilowatts are needed in order to have a detectable level of the minus density. Just to have an idea, in Spider a maximum of 800 kilowatts can be input. Also, the plasma drivers were selectively activated. Indeed, each couple of plasma drivers receives RF power by a separate generator. In this case, by activating these 3 couples of plasma drivers, and with a total RF power of 240 kilowatts, negative ion density of 8.8 per 10 to the 15 d minus per cubic meter was obtained. By switching down these couple of drivers, a reduction of minus 38% in negative ion density was observed. And by switching off another couple of plasma drivers, a total reduction on minus 58% was observed. The main conclusion from this is that the plasma in the expansion chamber can diffuse towards the plasma grid over a large area compared to the simple projection of the plasma drivers, which are shown here as orange circles. At last, it was observed also that the D- production is influenced by the magnetic filter field, which is made to reduce the electron density and the electron temperature. As it is expected, by increasing the filter current and then the magnetic filter field, it is possible to reduce the electron temperature and density, and so the electron stripping reaction are reduced, and so the D- are in a much higher density. However, as you can see here, there is a slight reduction when the filter current is excessively increased. This can be explained by the fact by an excessive reduction of electron density and temperature might lead to a reduction of those volume reactions that lead to the production of negative ions. So, in conclusion, the CRDS diagnostic in Spider was successfully developed, built and aligned, and now, from October 2020, it is routinely active during the experimental campaigns. The sensitivity of a diagnostic is of about 5 per 10 to the 15 D- or H- per cubic meter, which is already sufficient to study cesium-free operation and even better for cesiated operation. A basic characterization of negative ion production with respect to the basic source parameters was performed and here presented. In future, the mechanical stability of a diagnostic will be improved, and also efforts will be made in order to remove the drift in the decay time in order to study longer and longer plasma pulses with better accuracy. Also, 3 additional lines of sight will be added to characterize the spatial distribution of negative ions. Thank you for your attention, and goodbye.